All right, let's talk about the AWS Virtual Private Cloud, the VPC. Look, this is a topic that trips up so many developers, but stick with me. I promise, by the end of this, it's all gonna click.
So here's the thing. There's a reason VPCs feel so complex. If you've ever been pulling your hair out trying to get AWS networking, you are definitely not alone. See, most people try to explain it backwards. They start with this giant abstract VPC thing and go top down, but that's just not how we think, and it's not how we build.
So, let's flip that on its head. We're going to build this thing forwards, from the ground up, solving one little problem at a time. And it all starts with the absolute most basic thing we have in the cloud, a single EC2 instance, our little virtual server. It's there, but, well, it's kind of homeless right now.
Right, so this server can't just be floating out there in the ether. It needs a home, a specific location with a mailing address, that's what a subnet is. It's like a neighborhood. Your whole VPC is the big plot of land you own, and the subnet is the specific neighborhood where you build your house.
Now, what's really interesting is that not all neighborhoods are the same. We need different kinds. We set up public neighborhoods or public subnets for things that need to talk to the internet directly, think web servers. And then we have private neighborhoods, private subnets, for the stuff we want to keep locked down and safe, like our precious databases.
Okay, so our server has a house in a neighborhood. It has an address. Great. But it's totally isolated. It's like living on an island with no bridges or boats. It can't talk to anyone. It can't get any messages. So how on earth does it actually communicate? And that brings us to the next piece of the puzzle, the route table. Seriously, the best way to think about this is as the GPS for your network. Every single subnet gets one. It's just a simple set of rules, or routes, that tells all the little data packets, hey, if you're going to this destination, you need to go this way.
But here's the catch. By default, this GPS only knows about local roads. It has the map to get from, say, our public subnet to our private one, and back again. That's super important, right? It means our web server and our database can chat. But that's it. The GPS has no idea how to get to the wider internet. It's a completely closed-off system.
So now we have two really critical problems we need to solve. Problem one, how do we get our web server in that public neighborhood connected to actual users out there on the internet? And problem two, how does our database, tucked away in its safe, private neighborhood, get critical software updates without, opening the door to the entire world?
The answer is, we install two very different kinds of gateways. For our public subnet, we attach something called an Internet Gateway, or IGW. This is basically the main entrance, a huge two-way door to the internet. Simple enough. But for our private subnet, we use a NAT gateway. Now, this thing is clever. Think of it as a one-way security door. Data can go out, but nothing from the internet can just decide to come in.
And this is the brilliant part of how the NAT gateway keeps things safe. Let's say our database needs a security patch. The request has to start from inside the private subnet. It travels out through the NAT gateway, which lives in the public subnet, and then out the main internet gateway. The update server on the internet, it only ever sees the NAT gateway. So when it sends the patch back, the NAT gateway accepts it and knows exactly which private server to pass it along to. The key is the conversation can only ever start from the inside. It's a fantastic security model.
Okay, progress. Our network is connected to the outside world in a smart way. But connectivity without security is, well, it's a disaster waiting to happen. We need firewalls. We have to control who is allowed to even knock on the door. So AWS gives us two layers of security here, and understanding the difference is absolutely crucial. First, you have security groups. Think of these as the bouncers at the front door of each individual server. They're stateful, which is a fancy way of saying if you're on the list to get in, they automatically know to let you back out. Then you have network ACLs, or NACLs. These are more like the security patrol for the entire neighborhood, the whole subnet, and they are stateless. This is a big deal. It means you have to give them explicit instructions for traffic coming in and for traffic going out. All right, we have all the building blocks in place. We've got our neighborhoods, our GPS, our gateways, and our security. Now for the fun part. Let's follow a single packet of data on its journey, from a user's web browser all the way to our database and back out again. I promise you, this is where it all comes together.
Okay, here we go. Step 1. A user somewhere out there wants to see our website. Their request flies across the internet and hits our front door, the Internet Gateway. Step 2. The VPC's main router checks its route table, our GPS, and says, this is for the web server, send it to the public subnet. Step 3. Before the packet can even get into the neighborhood, it has to get past the security patrol, the network ACL. Step 4. It passes and arrives at the web server's front door, where it has to get past the bouncer, the security group. Finally, it's in. The web server looks at the request and goes, okay, to handle this, I need to get some information from the database.
And the journey continues. The web server sends a new request, this time destined for the database. The local route in our GPS points it toward the private subnet. But wait, it hits another checkpoint, the private subnet's NACL. It passes that check and then arrives at the database server itself, where it has to get past its own security group bouncer. Phew, only after all those checks does the database get the request. It grabs the data and sends the response all the way back through every single one of those checkpoints until it finally reaches the user. It's a multi-layered security onion.
And there you have it. You see? When you build it up from the ground, one piece at a time, it's not some big scary monster, it's just a logical sequence of solutions to problems. And hey, if this is the clearest explanation of a VPC you've come across, do me a favor and hit that like button and subscribe to DevOps Corner. It really helps.
So in just a few minutes, you've actually mastered the 5 core pieces of a standard VPC. Let's tick them off. Subnets, route tables, gateways, security groups, and network ACLs. That's the whole shebang.
But here's the real key takeaway. I really want you to remember this. Every single one of those components exists for a reason. It was created to solve a very specific problem, addressing routing, access, security. When you understand the why behind each piece, you don't have to memorize rules anymore. You have a mental model that lets you build, and maybe even more importantly, debug any network you come across.
So, we've built a really solid foundation here. But what happens when our website gets super popular and we need more than one web server? Well, that's what we're tackling in the next explainer. We're going to dive into how AWS load balancers work to spread traffic across all those servers, which is a total game changer.
So I'll leave you with this one final question to think about. Now that you see how all these pieces fit together from the ground up, what's the very first thing in your own cloud architecture that you're going to go back and re-examine with this new perspective? Let me know what you think. Thanks for tuning in.